So let me play with the lights a little bit here.
Okay.
So you thought the previous one was too dark, yeah?
Yeah, I think so. I'm not sure what everyone else thinks.
But this is much more romantic. Is it all right for you?
If you prefer that, that's fine, yeah.
If you prefer this, you're the boss.
I prefer a bit brighter, but I don't mind.
My brilliance is not enough for you. Okay. Loud and clear. I don't want this one though, so I think I definitely want to kill the ones close to the projector. Jack, I want to introduce your student.
Yeah, so this is Henry. He's done a project with me about Mackey functors. It's an introduction to kind of category theory and how it comes through now.
Yeah. So hello.
Let's also mention that you are a first year.
Oh well,
starting your second year.
Second year now.
So yeah. Let the record reflect.
Yes. Hi everyone. I'm Henry. Lovely to see you all. Thank you for coming. Yeah, I just want to say thank you so much to Jack. He's been really great. And like he said, I've been studying this idea called Mackey functors. So yeah, if you're wondering why I have cotton wool in my ear, it's because I recently had an operation. So don't worry, I'm fine. That's that. So yeah. Okay, so what I'm going to try and talk about today is explain to you what a Mackey functor is and how we define Mackey functors. So it's kind of an introduction to Mackey functors. It's quite a broad, deep subject. So it's just an introduction today. So yeah, so we may have a group G, and it will have a series of subgroups. And of course, each subgroup we will have a series of properties which we can investigate. So we can look at things like the order of the subgroup, etc., the number of elements which are acted upon when the group acts on a set, etc. And we may want to investigate how these properties change between the subgroups. Okay, so we might want to find a map between the change in property. Okay, so this is a brief explanation of what we're trying to do. It's a Mackey functor is a tool, or a kind of suite of tools, you could say, that a mathematician uses to kind of discover the relationship between different properties of a group and its subgroups. Okay, so we can look at a little example of that, so it's perfectly clear what I'm trying to say. So we might consider the cyclic group of order 4, and it has its two subgroups, C2 and the trivial subgroup. And we may want to consider the kind of size of these subgroups. So we could write a sketch like this, which is just showing you that there is some kind of relationship we can draw between this property of the subgroups. Okay, so the question then becomes, how do we turn this into a real mathematical concept, rigorously define it, so we can talk about it easily. But before we do that, we do need to spend a little time on category theory, because it's absolutely essential for what we're trying to do. So I'm going to try and give you a whistle-top tour of category theory. So the basic definition of a category is actually quite a simple thing. It's an object which has two types of thing in. It has a series of objects, and it has morphisms between objects. Okay, so these objects could really be anything, and the morphisms can be thought of for now as kind of maybe a mapping between a set. Okay, so you can think of it like that for now. And then there's these only two rules we need to obey, and we need to make sure that for each object in a category, there is an identity morphism. So we're kind of used to this idea of identities from group theory. And then we need to make sure that each object has an identity morphism, and also that composition is also defined well. So if we have two compatible morphisms, we need to be able to find a composition between those morphisms. So if we're going from A to B, and we have a morphism from B to C, we need to be able to find a morphism from A to C. Okay, so we can think of some examples of categories. The nicest one to think of, the most simple one to think of, is probably set, which is an object which contains all of the possible sets and all of the possible mappings between the sets. Okay, so we can also think of the category of abelian groups, which is all the abelian groups, unsurprisingly, and all the homomorphisms between the abelian groups. Okay, and there's some other interesting examples there. I like the category of small categories. It's quite interesting, and it kind of shows how powerful category theory can get. Okay, so that being said, let's dive into our first, or one of the ways we can define a Mackey functor, and that's as a function with a series of axioms. Okay, so we're considering a Mackey functor in relation to a group. So it's a G Mackey functor, and we're going to say it's a function from the subgroups of G, which does include G, to the abelian groups, and it's to an abelian group in this category of abelian groups. Okay, so each subgroup gets assigned an abelian group. Now we want to kind of replicate that little example earlier of each abelian group having some kind of mapping between and relation. So we're going to say that we need to kind of name certain morphisms or homomorphisms in this case, in the category of abelian groups. Okay. So we have three types. We have a transfer, a restriction, and conjugation. Now the transfer is when you're kind of going from a smaller subgroup to a bigger one. The restrictions when you're going from big to small, and the conjugation is something that we need due to some more technical reasons, which I'm not going into today. So we've got these morphisms which we kind of named, and these morphisms all need to satisfy a series of axioms. So here's a list of 7 axioms that these morphisms must abide by. Now, some of these look a bit complicated, some less complicated. Most of them are actually quite simple ideas. So, and things that mathematicians come across all the time. So, for instance, if we're kind of restricting from a subgroup H to K, then we're restricting again from K to J, that's the same as restricting from H to J. Okay, so that makes a lot of sense. The one that doesn't make sense, though, is the one at the bottom there. That is called the double coset formula. And there's all sorts of interesting reasons, or there's an interesting way of figuring out why that must exist, which unfortunately we're not talking about today. But yeah, that's a very interesting one there. Okay, so let's think of an example of a Mackey functor. And I said Mackey functor is a suite of tools because it depends on what property we're considering. So the constant Mackey functor is concerned with kind of this size idea, almost, as we were talking about earlier. And by definition, it maps all the subgroups to the same abelian group. So considering this was C4, we're mapping all to A, the same abelian group, doesn't matter what it is. And then we must figure out what our morphisms are. So restriction in this case is the identity map. So as it turns out, this restriction is a map from A to A. So the domain is a subset of the codomain. We can create this identity map, which basically is just mapping to the same element from the domain to the codomain. Okay, so it's basically just the identity. It does nothing. So that's often the case with restriction when the domain is a subset of the codomain. A bit more interesting is the transfer morphism, which is kind of getting at that growing and showing this kind of revealing how the subgroups grow in size. So here we define it as multiplying by the index of K in H. Okay, so we can see there that if we're going from the identity to C2, we're multiplying by 2 because it's doubled in size, and then again C2 to C4 is doubled in size. Okay, and it turns out the conjugation is just identity up here because these are all normal subgroups. Conjugation isn't doing anything. Okay, so I think, yes, this bit next. So we have this one definition of Mackey functors. There are actually a couple more. And it's all well and good having a nice list of what decides is a Mackey functor, but it's also nice to have a way where Mackey functors is a more kind of automatic thing, where by definition it creates these transfer and restriction morphisms. So a brief moment on functors. Functors are maps between categories. So if we have a category C and D, a functor's job is to create an association between the objects of the two categories and an association between the morphisms of each category. So for each object in the kind of domain, we need an object in the codomain, etc. Same for the morphisms. And also we need to make sure that composition doesn't kind of break once we apply our functor. So we can create kind of like a function between categories. It's called a functor. And An example of a functor could be the forgetful functor, for instance, which is a nice simple one to think of. It's a functor from groups to sets. And essentially what it does is it strips the binary operation off the group. So if we have a group which is defined using a set and an operation, the set is S, then this functor will just take that and output S, okay? And then the homomorphisms in group are just basically mapped to the same thing in set, but it's like not a homomorphism, it's a set map instead. So we have this list of axioms, but there is a kind of better way to describe Mackey functor, where we can describe it as a functor from a certain category we need to figure out, where we can kind of describe it as a functor which automatically has these restriction conjugation morphisms in AB, okay? And this was kind of where my project got up to, and it was this kind of final definition we came across, which was to and this is the whole definition, including all the axioms in basically just a few lines, basically. So it's quite a nice definition here. It's this special type of category called a span category on the category of finite G sets to the category of Abelian groups. And yeah, that is basically what a Mackey functor is. So yes, thank you very much for listening. It's been really fun. Thank you for this opportunity. Any questions?
Jack, ask me a question.
So could you go back to the example of the Mackey functor that you wrote there, the constant one?
Yeah.
A couple of slides along, sorry. Yeah, so the transfer morphism, so you said the restrictions are just like the identities.
Mm-hmm.
So in some sense, the first guess for me for the transfers would also be to choose the identity maps for the transfers. So why do you choose the multiplications?
Yeah, so it's all done to the axioms, I believe. It will turn out that if you try doing that, I'd imagine the axioms wouldn't hold. So this final axiom here, called the double coset formula, it's quite an interesting piece of criteria. It makes it more strict what the axioms are, but it also means you can use it to actually discover what the morphisms must be. So we did an exercise where we kind of broke this down into a more simple state where we picked the subgroups very specifically, so we could simplify this massively, and it actually popped out what the transfer must be. And it's really interesting. It's an interesting mix between like that being the definition of the constant Mackey functor, and also kind of as a result, it's the only thing that would work in the when you pick when you define it in this way. That's my understanding. Yeah.
My understanding too. Sure.
Yeah, can you go back to the same slide we were just at with the transfer contract? Example? Yeah, this one.
This one, yeah.
Yeah, so maybe the answer is obvious. I don't work with groups that much, but so in a group, you have group elements, you have inverses.
Yeah.
Why can't you multiply with a scalar? Don't you need some kind of algebra structure for that?
Well, I believe it'd be because we would have to pick an abelian group which had where 4 and 2 are elements of that group. I would imagine.
I mean, all abelian groups are modules over the integers. So, so they have scalar multiplication from things in the integers.
Okay.
Yeah, the actual original definition of this in the paper, it was actually mapping to R modules, but I changed that because in the final definition it is abelian groups, and it's just kind of didn't want to kind of confuse people too much, so simplified it by doing that. Yeah.
Seen any application to topology or something?
Well, it has applications to pure things, applications to the real world. I'm not so sure.
No. I wasn't even that ambitious.
No, it does have lots of applications. I believe it's called stable homotopy theory. It's one of them. Representation theory. Lots of things that I have no knowledge of.
If you were to, try to imagine what an application would look like.
In pure maths.
Yes, I mean very vague.
Well, it kind of, I guess, a Mackey functor kind of helps you see how the kind of what a subgroup can do, how that changes through a series of subgroups, and there's lots of different Mackey functors. But I guess maybe it means if you know something about one subgroup, and you kind of know relationships to other subgroups, you can find about things about other subgroups potentially. Maybe.
Is it only applicable when you down finite subgroups, finite groups? And
Is it only applicable to finite groups? Well, I imagine I imagine infinite groups work as well. They'll have subgroups, won't they? So
I think it needs to be compactly, so you can take like close subgroups.
Yeah.
The first question as well, like they're very refined invariants of things. So like group cohomology groups are Mackey functors. So you might have two groups that have the same cohomology, but they might have different Mackey functor structures. So that allows you to distinguish the two groups from each other, for example.
Use like an invariance.
Yeah,
Yeah. Okay.
well, thank you very much.
Thank you.